Welcome to Introduction to Magnetic Fields, which is the first in a series of short videos about electromagnetism. Now, these videos are not designed to cover everything you need to know about the course, but they do provide you with the basic notes and cover all the main concepts and definitions and equations and some of the basic ideas. You are most likely all familiar with magnetic fields. You've all likely got a fridge at home and use magnets to stick them on there. You've played with magnets when you were kids. You may or may not have used a compass, and what you're doing there is using a magnet to help you determine which way the Earth's magnetic field is pointing, unless you're like my kids and use them as a toy and make them spin around. Anyway, magnetic fields you're familiar with, but you may not be familiar with how we describe them.
Magnetic field is a vector, so it has a magnitude and a direction.
They have a symbol. That symbol is the letter B, large letter B, and they're measured in a unit of Tesla. Now, the Tesla is quite a big unit. 1 Tesla is a very large magnetic field. So sometimes instead of Tesla, we use the unit called a Gauss. 1 Tesla is 10,000 Gauss. So now we're going to talk about drawing magnetic field lines. So here's your classic magnet, a bar magnet, and it has a north pole and a south pole. Magnetic field lines come out of north and into south. So I've just drawn some field lines to indicate what direction the magnetic field is pointing at any particular point in space. So if we chose a point in space, say here, the tangent to that curve would give you the direction of the magnetic field at that point in space. Magnetic field lines coming out of north, you can see that there, out of north. These would eventually loop around and come back into south, so they don't just end there and they don't go off to infinity. Now, I've been very specific about how I've said that. I've said they go out of north and into south. You may have heard them described before as going from north to south. Say you had 2 magnets next to each other. When we're talking about a bar magnet like this, they go out of north and into south, and that's actually true. They go all the way through the magnet as well. The magnetic field exists inside the magnet. In fact, the magnetic field lines have no beginning and have no end. They just loop around inside and outside of the magnet. If we put another magnet, say another small bar magnet, somewhere near this magnet, we can probably predict what happens if we put the magnet down here. So we've put a magnet down here. We know, or you probably know from your previous experience with magnets, that like poles repel, so a north will repel a north, and unlike poles attract, so a north will be attracted to a south. And that's exactly what we see when we put this small magnet in the field created by this existing magnet. So I've just drawn that little red side to the magnet to show that that's the north end. The reason that it does that is because magnetic field lines of a magnet like to line up with the existing field. So I'll just draw the magnetic field lines around this tiny little magnet here. It's a little bit hard to see, I'm sorry it's so small, but you'll see that in this region of space down here, the magnetic field lines are coming out of north, so they're pointing up the page, and they're lining up with the magnetic field lines that are coming into the south pole like that. So magnetic field lines like to line up, so they will do that. And again, down the bottom here, they're coming up the page, so they're lining up with the ones that are coming up the page. What happens though if we put a magnet in this existing magnetic field over here? So there's our magnet. We know that the magnetic field lines want to line up with the existing field, so they're going to be coming out of the magnet that way and into the magnet that way, and of course looping round as they do. That's a bit of a mess. So they're coming out of the bottom and into the south, which means this magnet's north pole is down the bottom. It's facing downwards. So there's our magnet out the side here. It's actually pointing the other way because its magnetic field lines are lining up with the field there. And this is the basis for the compass and how a compass works in the Earth's magnetic field. And in class we'll be talking more about the Earth's magnetic field and what it looks like and how a compass works. Just another bit of notation really is how we draw the magnetic field if we're looking not side on to the magnet like this, but we're looking, say, into the top end of the magnet or into a pole. So here's our magnet. Just say this is the north end of the magnet, looking down on the north. I'll just write that there. So we're looking down the end of the magnet. What will we see? We'll see field lines going out of north, so they're coming towards us. So it's like we're looking at the arrowhead. We're looking at a point, so we draw that as a point, a dot. But in the region surrounding the magnet, the field lines are going away from us, so it looks like the cross feathers on the back of the arrow. So we'll draw crosses to show the magnetic field is going away from us in that region. And this is a common way of showing vectors that are coming into the page or out of the page. And there's a basic introduction to magnetic fields, and we will of course cover more in class.